Yeah, oh, we need to allow it.
Okay,
You can use that voice. They're on the gallery if you're prepared.
hello, testing. Okay. Okay, great. Sorry. Thanks so much for the kind introduction. I'm super excited to be here today. I'm Tyler Hayes, and I'll be talking about adapting to the unknown, lifelong learning, novelty, discovery, and beyond. I'm sorry that I'm over here. My laptop cord doesn't go any further, so I'll try to keep it engaging. So most of us are here because we think adaptation is crucial, and it may come in many different forms, right? So in the upper left-hand corner, maybe you put on your favorite pair of AR goggles and you'd like to be able to have them adapt to your own preferences. Maybe I'm walking around my home and I'd like them to be able to understand my personal home environment, learn my pets' names. You know, I say, oh, where is my cat? Briscoe, and then it tells me where they are. Or maybe we've worked on things like domain adaptation, where you've trained on a bunch of classes and you're trying to identify those classes within changed semantic conditions, right? So maybe now it's snowing or the lighting conditions have changed and we'd like our agents to be able to identify the objects within those new scenarios. On the right, I'm proposing a different type of generalization that I'm still calling adaptation, but maybe it's operating in a slightly different way, right? So maybe during the training phase, I've learned about horses and I've learned about the concept of striped. And at test time, I say, okay, a striped horse is a zebra, and I provide it with this image and I ask, can you now identify what this object is based on this contextual understanding from the text? Or maybe during training, you've seen red tomatoes and yellow bananas, and now during test time, you'd like to be able to compose those concepts to learn about yellow tomatoes. So this is kind of the premise of my talk, is these two different scenarios. The one on the left, which is probably what we're classically calling continual learning, is what I'm going to refer to as dynamic adaptation scenarios. And on the right is more of static adaptation scenarios. So you might be asking yourself, well, how do we actually adapt our models in these two different types of scenarios? So dynamic adaptation, again, is what a lot of us refer to as typical lifelong continual learning. So this is where we're adapting the model on the fly to an incoming stream of inputs as they're becoming actively available. So this is our classical scenarios like lifelong learning, which is done in a fully supervised way, or even things like open world learning or novel class discovery, where maybe the inputs are coming in. The agent has to identify whether it knows it from, being pre-trained on it, or if it's a new input, and then gradually update to those, like in novel class discovery, in an unsupervised way to now identify those inputs. In contrast, static adaptation is what I'm arguing is preparing the model in advance for unavailable semantic concepts. So this could be something like I pre-train a large vision language model, I train it on a bunch of different semantic concepts, and then maybe at test time I have to generalize in a composable way to unseen concepts, right? So I'm using the same example from before. We learned about stripes and horse, and now I'm using the shared vision language space with a language prompt like a zebra is a striped horse to be able to compose that knowledge to adapt. So we can kind of identify the space of problems and methods under one generalized framework based on what has changed, what data is available, what priors are being assumed, and how are we actually using the data. So what has changed? A prior change could just be something like my label distribution is shifting, right? Maybe now I trained during pre-training on a balanced distribution, and now all of a sudden I have a long-tailed distribution. Or things like covariate shift, which is typical in domain adaptation. Maybe I have a fixed set of classes that I've learned about, but the semantics around the scenes are changing, right? Maybe now it's snowing, whereas before my agent was trained during the fall, so there's leaves and things like that around. Or a lot of us are familiar with semantic distribution shift, where my label space is actually changing, right? New classes or categories are becoming available over time, and we'd like our agent to be able to adapt to those. We also have to consider things like what type of data is available. Is it supervised? Is it unsupervised? How are we going to handle that and evaluate in those particular types of scenarios? And also what types of priors are assumed. For static adaptation, it's not just adapting in a magic way, right? We're assuming some type of prior to be able to adapt, as I'm calling it. Some of you might disagree with this definition of adaptation, which was a conversation last night at dinner, but I argue that priors like compositionality or a vocabulary, which is a language-based prior, could help our models adapt in a different way. So a lot of us are familiar with relevant paradigms that I'm putting up here, and I've just kind of put them into this framework, right? So test time adaptation or domain adaptation, we have a covariate shift and it's done in an unsupervised way. A lot of us are familiar with lifelong or open world learning, where we have a semantic label distribution shift in a supervised scenario. Or we can even go one step further in novel class discovery, where we have a label shift, but then we're doing fully unsupervised identification of those categories after we've identified them as unknowns. In contrast, we have paradigms like static adaptation, which are things like compositional zero-shot learning, where the compositionality of the feature space is something that we're using in order to adapt, or things like open vocabulary learning, where we have, again, a shift in the label space, but we're using a vocabulary in a shared vision language pre-training phase to understand generalizations. So today I'm going to be talking about two of my works, where one of each of them fits into each of these paradigms. So one of the works will be on novel class discovery and the other will be on open vocabulary learning. There are pros and cons to each of these, and some of you might argue that the static adaptation might not truly be adaptation. We can discuss that more later. But dynamic adaptation, it doesn't solely rely on pre-collected data, right? You could start with a base trained model, but you could also just learn on the fly as the data becomes available. And this makes it more flexible, right? As the data is coming in, I'm allowing my agent to actually adapt to that data as it's becoming available. On the other hand, this might have slower inference, because inference also might encompass this phase of actually having to update on that new data before I can actually evaluate my agent on it. And we're going to influence heavily based on what data is becoming available, right? So this could relate to catastrophic forgetting, where maybe the label distribution has changed so much that now you're forgetting about things from the past. In contrast, static adaptation is all about the data. If you don't have good data, you're not going to generalize, right? Or if the prior is not assumed of compositionality in the case of compositional zero-shot learning, or a shared vision language space in the case of open vocabulary learning, then you won't generalize. But perhaps you have faster inference because you're not necessarily adapting to new data as it becomes available. You're doing something special like composition or using that language in order to generalize. So these are some pros and cons of each, and obviously you could combine the two approaches, but this is kind of the framework that I'm operating under. So let's dive into a dynamic adaptation case scenario by talking a little bit about novel class discovery. So my motivation here is that the world is open. Incremental or continual learning is interesting, but again, we live in an open world, and it's probably important for our agents to be able to identify unknowns. So let's assume in figure A, right, we have a closed set object detection framework where basically we've trained our agent to be able to identify different classes such as dog, bird, and cat. It puts a box around them and we say that those are the objects. Open set object detection takes this one step further, and you can see that we've now also put boxes around the things that we don't know, and we say those are unknowns. Novel class discovery takes this a bit more extreme, and it says not only do I have to identify that those are unknowns, I also have to group them into respective categories in an unsupervised way based on shared meaning. So this is kind of a little bit about how a novel class discovery works. So maybe we're given some discovery set, and our agent has been able to identify or put boxes around objects that it discovers. And then the goal is to create these clusters that basically represent different concepts or classes that can then be identified within a test image, where I'd say, this is discovered class 1, discovered class 2, and discovered class 3. And up to you, you could add a semantic label for human intervention if you'd like. So to that end, I'd like to talk a little bit about this paper that was actually published at CoLLAs last year, which I unfortunately was not able to attend. This was work that was performed at Naver Labs Europe with a bunch of my colleagues. So the novel class discovery pipeline consists of 3 phases. The first phase is a base phase where we learn the parameters of a detection model on an annotated base set. So this is a standard supervised training, pre-training phase. We then perform a discovery phase where we're basically given a set of unlabeled images, and the model must identify or group novel classes together while also remembering base classes, right? So the base phase looks a little bit like this, where we're identifying birds, dogs, and elephants. And then during the discovery phase, you can see that we're still identifying birds while also grouping things like zebras and horses together into their own semantic groups. at inference, this is the goal, is that if I identify an object as a base class, I have to provide the actual label for it. And if I identify it as a novel class, I have to provide the ID of the cluster that it actually belongs to. So to this end, we proposed this pandas method. Of course, it has a cute name, prototype-based novel class detection and discovery. So in the first phase, we basically pre-train a faster RCNN model on the base classes. And then basically what we do is we pass those base images through the detector and we extract boxes for those objects in the image. We can then select the boxes that correspond to ground truth, and we can actually take the mean across classes to form a group of base prototypes from the features from those boxes. During the discovery phase, we then use this pre-trained backbone and region proposal network to actually propose boxes in the new images. We can then extract the features from those boxes and perform a simple clustering. You can use your favorite method. We used k-means because it works really well here to basically form a bunch of prototypes for the novel classes. The real interesting part with this method is really just the inference where we're doing prototyped or similarity-based assignment of those labels. So basically you pass a test image through, you get boxes and their features, and then you can compute a similarity score of all of those extracted features with these base and novel prototypes, filter out those that you might think are background boxes, provide a score, and then continue in your standard object detection setup. To assign a semantic class to the novel prototypes at test time, we follow prior work and we use Hungarian matching to actually map the discovered prototypes to class labels to do evaluation. So it's a very simple method, but we were very curious because the prior state of the art was this RNCDL method, which actually used SWAV with pseudo labels and a supervised loss to perform novel class discovery. So you might be thinking, why are you doing something so simple like prototypes? But we were really wondering, these existing methods that had all of these different components, are they all actually necessary, or can we get away with a simple baseline? And the answer is that we can get away with this simple baseline and outperform this existing method. So the benchmark we were using here is CoCo to LVIS. If you're not familiar, CoCo and LVIS are based on the same set of images, but they have labels. CoCo has labels for 80 classes. LVIS has labels for 1,203 classes. And so basically you treat CoCo as the base set, and then you generalize in the novel class way to those classes within the LVIS data set, which is also long-tailed. So I'm providing the performance on the base classes, the novel classes, the all classes, and then frequent, common, rare. You might argue that the performance is pretty low on novel classes. I have to admit that I think that this is partially due to the lack of labels in the LVIS dataset, which I'll show you in just a little bit. But all of the variants of our method were able to outperform this very complicated RNCDL method while also running over 5 times faster. So a simple baseline was performing much better than the more complicated object detection method here. So it's more interesting in novel class discovery and things like this, I think, sometimes to look at the qualitative results rather than the quantitative results. So I'm visualizing 3 semantic class names here that were mapped during the Hungarian matching phase. So on the top, you're seeing hot plate. It's correctly identifying some of the hot plate images, but you can see it's also confusing things with stove. In the middle, it identified this as a cylinder, but what it actually is a fire hydrant. And again, this is a problem with this Hungarian mapping matching scheme. So it's just kind of interesting to look at this. And again, we can look at some more visualization. So on the left, I'm showing you the ground truth, and on the right, I'm showing you what our novel class discovery method identified. And you can see that there's a lot of things that are not actually labeled in the ground truth that are actually identified by our method, right? Like snowboard, skis, ski boot. I would argue that these are correct and they're just missing from the actual ground truth. So maybe this is a reason not to use this LVIS data set, but it could provide an interesting way in the future to make automatic annotation pipelines for these methods. But beyond novel class discovery, there's also alternative ways to adapt to unknowns. So one way to do this is what I'm arguing is that static adaptation paradigm that I talked about before, and we can do this using vision language models to aid in the identification of unknowns. So in this part of the talk, I'm going to talk about static adaptation via open vocabulary learning. If you're not familiar with open vocabulary learning, it's basically a way of adapting models to unknowns without retraining on every single new object as it becomes available. And they do this by leveraging large vision language pre-trained feature spaces like those that come from clip-based models. The motivation here is that language data is a lot cheaper to annotate than masks or boxes. If you've ever tried to annotate an object detection or semantic segmentation data set, you know how difficult this can be. And the other is that language is more general and extendable, right? I can write a lot more about a description of an object than having to provide a bunch of images for it. So for this work, I'm going to present our paper that was published last year in CVPR. It was a highlight poster, and this work was led by our intern at Naver Labs. His name is Mew, and he led this project. So our motivation here is that standard open vocabulary object detectors only use the class names for inference in their vocabulary embedding. So basically the way that these models have been trained is you take clip and you embed the class names into the shared vision language feature space, and then you train the detector to align its classifier with this shared vision language space using those names that have been encoded with clip. But we asked the question, is there a more interesting way to actually encode these names, maybe using super and subclasses of those actual categories in order to aid the model with more information? So that's what we did in this paper. So the way that the Shine method works is kind of like this. So let's say that I want to encode the word bat, right? A standard open vocabulary model would just encode the word bat using clip, and it would use that embedding as the classification for that particular word. Instead, what we do here is we take some type of hierarchy. This could come from a ground truth in a data set, or it could come from an LLM. And then basically you find all of its superclasses. So here you can see that a bat is a type of sports equipment, and then there's specific types of bats that are subclasses, right? So things like baseball bats or cricket bats that are made of different materials or have different properties. And then we encode them basically as a bunch of sentences like a wooden bat, which is a baseball bat, which is a bat, which is sports equipment, and things like this. And then we can actually pass those sentences through the text encoder instead of just the raw class names to get a bunch of embeddings. And then we can aggregate those together to form a more informed feature vector that will be used for classifying the bat class in this case. So our main results are performed with the DDIC method that uses a ResNet 50 backbone and the clip vision language space. We also tested this with a bunch of other detectors and backbones in the paper. I'm just showing one main result here. We compared a baseline of just encoding those raw text names with using a large language model generated hierarchy as well as a ground truth hierarchy. And we compare the performance across different granularity levels, right? So I'm infusing this superclass and subclass information. So we use data sets that have, you know, super and subclasses. So I can test at those different levels, right? Like I could test at the bat level, or I could test at the sports equipment level and things like that. And so basically level 6 is more fine-grained, level 1 is more less fine-grained, more coarse-grained. And you can see that even the LLM generated hierarchy performs quite a bit better than the baseline, right? We get up to 28% performance improvement just by using this hierarchical information fused into those embeddings. We perform this on 2 different data sets. So we use the iNaturalist data set, which is fine-grained biology images, and FSOD, which is a standard object detection data set. And we found that the method worked really well for these fine-grained biology images. So it's sort of interesting to think about using open vocabulary learners that have been trained for generalized vision tasks for more fine-grained tasks like biology here. Yeah, so it improves granularity, robustness, and overall performance. But one of the things that's sort of a limitation in both novel class discovery and open vocabulary learning, which I'm kind of alluding to here, is their notion of a reliance on a class. Classes are discrete, they have a fixed meaning, they're not necessarily correlated with the real world, right? They're rigid, non-overlapping, and sometimes I argue subjective. So instead, I'm arguing that concepts are more granular. They can lead to compositionality. We can have class or concepts that have multi-membership, right? Like many different bird species, they all have beaks, they all have feet, things like this. So they all share that, and they can even be relational. So for my future research, I'm very interested in this idea of concept-centric adaptation. And I want to give a shout out to Vineeth. I was unaware of this work, but he has worked a little bit on this and discussed this just a bit yesterday. So for concept discovery and learning, the notion of a class, again, is subjective and not necessarily correlated with the real world. This often comes up, you can think about how British English and American English, we use different words to describe the same thing, like a trash can or a bin, but we're really semantically talking about the same thing. So these are very subjective and not necessarily correlated. Instead, our world is comprised of concepts or parts, right? And these are crucial for understanding object structure, the compositionality of our world, and actual functionality, right? Maybe we see that in many different animals, they have legs and they're using these legs to move around. So concept or part discovery could maybe help us with fine-grained object discovery, maybe action understanding, and even things like robotic manipulation. So the goals for concept discovery and learning would be to automatically discover and refine hierarchies of abstract concepts over time, and then perhaps use those concepts to more easily complete tasks. Why do these concepts actually matter in lifelong learning? Well, models learn how the patterns are actually formed instead of just semantic class names, right? They have to learn a more granular level, so perhaps they're learning more fundamentally what actually makes an object and how they operate. Shared concepts among objects can lead to knowledge preservation, right? So maybe we have less forgetting because a lot of objects are sharing these same semantics instead of abruptly changing from, car to panda or something like this. There's also similarity in the concept space. So this could lead to improved transfer, and concepts can also be composed into classes. So this might help us quickly learn new classes. You could think about if I'm trying to learn a new bird species, but I already know about the parts of old bird species, it might be just a small step in my feature space to try to learn about this new bird species. Ways that we could think about doing this are part-based representation learning, disentanglement, or compositional reasoning and vision language feature spaces, like how we were doing that for open vocabulary learning earlier with super and subclasses in a hierarchical way. So just to wrap up, I'm arguing that model adaptation is critical, and I think that there's two different ways that we could approach this problem. The first is by dynamically updating to incoming streams of data as they become available. The other is statically adapting to things utilizing a pre-trained feature space, perhaps something like a vision language space and CLIP. Choosing our adaptation type is often application dependent, and it can, we can combine methods. There's no reason you couldn't combine that. I discussed two methods, one for novel class discovery and one for open vocabulary learning, that both adapt to new classes, but in slightly different ways. And for the future, I'm very interested in this notion of concept-based adaptation to make understanding more human-like and give us richer representations. So thank you very much, and I'm happy to take any questions that you might have.
Thank you for the nice talk. We have a bit of time for questions. Someone already has one here. Ross.
Thank you. Nice talk. I'm just wondering, what is the relationship with recent models like Segment Anything, which don't use class labels at all? Or how can such systems be used to sort of aid your research and learning these kinds of like structures and classes?
Yeah, that's a great question. Segment Anything came out while we were doing the novel class discovery work, and that could definitely be an alternative way for proposing boxes or segmentation masks in the actual images. And then you could apply like a novel class discovery method on top of those pre-extracted segmentation masks or boxes from something like SAM to do that. So yeah, I definitely think these more powerful unsupervised methods can definitely aid this problem, because then you can just focus on actually learning the classes or concepts instead of having to worry about the more granular problem of how do I put the boxes in the images. Yeah, good idea.
Thank you.
I really like the idea of this concept-based adaptation, but for real-world images. But do you think this kind of adaptation is also useful when your data is not understood by humans? Like you have a lot of biomedical data, physics data, and in this kind of way, you don't really need human-like concept because that's not ideal.
Yeah, that's a good point. I mean, I guess it depends on what your actual task is. I still think that even in other domains, like for example, earth science, right? We have hurricanes, but hurricanes actually consist of smaller patterns that are composed to form it. So maybe you can like learn those relationships in this more fine-grained way. For medical imaging, I mean, concept-based might have a different notion there. I guess it depends if you're talking about the relationship of body parts within a human or animal or something like this, right? Yeah, I would have to think a bit more about that. And I guess it depends what the actual application is. I mean, just like any other field, right? We don't always need to apply continual learning. We might not always need to apply concept-based learning. So I agree, like it's not always necessary.
Okay, thank you. Thank you for the nice talk. There's a question that I get asked, and maybe an open question beyond what we presented here is with LLMs and multimodal LLMs, is there anything like open world and novel at all? Right. So there's a question that I often get asked that, okay, is there something, I mean, that they don't know, for instance? Right. So just wanted to get your thoughts on what you think about that.
Yeah, and this is a really interesting point, and this is something we talked a lot about during that hierarchical open vocabulary learning paper. I mean, it is true that these models have seen a lot. I guess the question then becomes like, for example, using iNaturalist, right? Have they really seen and understood the fundamental hierarchy of the iNaturalist data set? Like, I can't even say half of the names of the object classes there because they're so fine-grained. But yeah, I agree that this does become a harder question of what is out of distribution for an LLM. And I guess it's really difficult these days because we often don't know what they were trained on. Yeah, I think, you know, fine-grained categories is one area. Instance recognition is another area, right? Like, I mean, they've been trained on the internet. Maybe I have a new cat or something, and I still would like to be able to identify my new cat. And so it shares features with this old one. But yeah, there are limitations, I guess, in terms of that, because it might not actually be adapting if it's actually seen it. Yeah.
Yeah, thank you very much. One thing I always wonder in novel class category discovery is like how, like, do you have some best practice on how to think about like the level of granularity that you are aiming for? Because yeah, you could do like whole object, but you could also go super fine grained, and like, is there a way to control it? Should you control that? Like, what's your take on that?
So in practice, I think most people control it to whatever benchmark they're working on, right? So in the case of LVIS, you're operating at the level at which LVIS was annotated, but I don't necessarily think that this is the right thing to do. And it's probably going to depend on what you're actually trying to do downstream. I'm arguing for the more concept-based approach where you do go more fine-grained, because then you could potentially compose it back into, you know, the actual objects or animals themselves. Yeah, I guess it's a question of what you're actually trying to do. I think many applications could maybe benefit from breaking things down more compositionally to better understand the actual parts and the shared structure among them. But yeah, I think a lot of people right now are optimizing to the actual benchmarks themselves, which is why I think that maybe getting away from just optimizing the benchmark and moving towards a more organic way of doing this makes sense.
Right, thank you. Yeah.
I have another question. All these like continual learning thing, you're adding new knowledge, let's say new classes and stuff, but maybe you don't need to update the weights of the network and stuff. Do you think, I don't know, in vision, for example, there is a need to update the weights, or is there, you could just have a concept detector which is frozen and then you're just adding new knowledge over time?
Yeah, this is kind of the premise of open vocabulary learning. So I do agree with you, but I think it goes back to Vineet's question of like, is it actually out of distribution if we don't necessarily know what it was trained on? In that case, I totally agree with you. And I think there needs to be some other prior that's assumed on that actual like pre-trained model that you're operating on. Is there some type of compositionality? Do you have access to a shared vision language space? I'm arguing that I don't necessarily think you always need to update the weights in order to generalize in those scenarios. Some people here might disagree with that, but like open vocabulary learning, compositional zero-shot learning, they're really built on this fundamental idea of a pre-trained network and then generalizing based on some other technique there. So I agree with you. Yeah, there could be a time that you don't necessarily need to update. And it depends on, you know, how much time you have for inference and the income, if you have incoming data and things like that.
Cool. Thank you.
Thanks for the wonderful talk again. Let's